grad students in our department, EECS department, that is forming a journal club. I think the journal club is centered around topics related to micro-nano systems. If you are interested in participating in the journal club, see Chris Roberts. There's no formal schedule of events yet set, so, but I think it's a really good idea. Aside from attending seminars, it's the best way to learn things outside, maybe directly applies to your dissertation area. So see Chris Roberts. Secondly, as we do every week, I'll be passing around the colloquium sign-up sheet. Make sure that you sign in so you get credit for attending the seminar. Are there any other announcements anybody would like to bring up in front of the body before we start? No? All right. So let me get the house lights where they need to be. How's that? Is that good for the videographer? Okay, good. Is that good for the speaker?
Sure.
All right, so without further ado, let me please introduce our today's seminar speaker, Professor Gianluca Piazza from the University of Pennsylvania, Department of Electrical and Systems Engineering, and he's going to speak to us today about some interesting topics in NEMS and NEMS, most specifically aluminum nitride-based devices. He comes to us, of course, by way of the University of Pennsylvania. Prior to joining the University of Pennsylvania, where he is currently the Wilth Family Term Assistant Professor, he did graduate work at the University of California, Berkeley, under the tutelage of Al Pisano, I think. And he also did research work in the area of aluminum nitride-based resonators, switches, and other RF MEMS-based devices. So, without further ado, turn the floor over to Professor Piazza.
Thank you very much, Chris, for the introduction and for inviting me and hosting me here at CASE. So as Krista said, I'm going to present a little bit about the work that we're developing at Penn in my group, looking at the aluminum nitride, piezoelectric, nano-electromechanical, resonator and switches. Really the scaling of the MEMS from MEMS to NEMS of many of the devices that we developed. And some of the devices might still look micro, but we're really pushing forward to really move into the NEMS realm. So a brief outline, a brief motivation of why scaling, right? Some people might still think that actually scaling is not so advantageous. Hopefully I'll prove to you that really making devices smaller is really not just a fascinating topic of research, but it's really something that can really impact our applications in our engineering world. And then a little bit about aluminum nitride as a piezoelectric transduction, as a preferred transduction for nanoscale devices. Then a bit about resonators for reconfigurable RF, three areas of application basically, reconfigurable RF, chemical and biosensing, and then the making of nanomechanical switches for a new area of mechanical computing. So the three key areas of research. So I'll give you a little bit of a brief overview, so if you have questions, feel free to interrupt and everything. I won't have a chance to go too much in details for each of the three topics. But I wanted to give you an overview of the three key areas, which is basically communication, sensing, and computing, in which we're working on. My group is working on at Penn. Then some concluding remarks and an outlook. So advantages of scaling. So why do we scale devices, right? Especially why do we scale resonators and switches, which are the two core devices that we're working on at Penn. And here you can see the three key motivators, the same motivators that are actually driving the CMOS industry, which is really speed, power, and size. We're moving from basically millimeter size resonators and switches to MEMS scale devices all the way to NEMS scale devices. Well, we move across sizes, basically 6 orders of magnitude about difference in size, with speeds that now move in the gigahertz, hundreds of gigahertz for the, hopefully hundreds of gigahertz for the RF part, for the microwave part, and power consumption that now goes in the microwatt, milliwatt for MEMS, down to maybe nanowatts at the nanoscale. And really, though, it's not just about power, size, and speed. All this comes with a set of applications that you're really enabling with these smaller devices, right? With these quartz crystals, with our mechanical resonators, basically at the millimeter scale, and mechanical relays, you are looking at off-chip application. With the MEMS scale devices, for example, here is showing a monolithically integrated MEMS switch with a resonator that we've done at Penn. where basically you're looking now more about system on a chip, system in a package, where you have the circuit and you have a few mechanical elements that are helping you doing some functionalities. And I think really the revolution will happen at the NEMS scale, where you can really think about the device becomes so small, like a CMOS transistor at that point, where you can look, or in comparable size, where you can really think about large-scale integration of these devices, where you're massively arraying now mechanical elements. You don't only have like 5, 6 mechanical elements, you have maybe 100, 1,000, or 10,000 of those. And then you can really do new things. You can make sensor network, you can take advantage of arrays, you can make reconfigurable mechanical elements, or you can make even computing elements with mechanical devices systems. So what I'm trying to talk about today is showing you a little bit of what we've done at the MEMS scale and some of the initial leap toward the towards the NEMS scale. And 3 key areas of application, as I said, one is really this reconfigurable transceiver, in which we basically use banks of filters and banks of switches with banks of mechanical oscillators that can now be connected and interface with circuits, and now can be reconfigured on the fly. So you can have multiple frequency, multiple bands, which might be used for sensor networks, right, operating over different frequency bands, even wireless devices, other type of wireless devices for like biomedical application. And scaling also opens up an entire new challenge at the microwave, where these mechanical elements are about 1,000 times smaller or more than existing microwave components. So you can imagine making devices that now are substantially almost acceleration and vibration insensitive. And so they could operate much better than existing, microwave devices that are generally bulky, pretty big, and they're subject to acceleration and vibrations. So same thing in the sensor array. The sensor world is really about making arrays, I think. I'll show you when I talk about the details of the sensor. The sensor are not going to be better in terms of performance, actually. I don't think we'll gain in terms of ultimate limit of detection. We'll expect even to macro scale devices. What we're really going to gain is the type of application where now you can think about making mechanical noses, basically electronic noses, formed by large arrays of these devices. But then you can have personalized healthcare, environmental monitoring, basically threat alert and so forth in a portable fashion, even in a disposable fashion, possibly. And then last is creating these mechanical relays at the nanoscale that could really revolutionize the way we make transistor in terms of power consumption. Probably not in terms of size, but at least in terms of power. If you can make a millivolts transistor now, but basically with a VT, a threshold voltage that is sub 1 volt, well, you can have power consumption now, not only in the standby state, basically in the off state, where the leakage is a given. You have an air gap instead of a solid channel. So for sure, you're going to lose less power, but also you want to lower power consumption in the on state. And this is really where I think the NEMS technology can play a role. So these are the key 3 areas, I think, in which we're operating. Then the biggest challenge is how you move these devices, though, at the nanoscale, at the micro and nanoscale. And I'll try to motivate why we've used aluminum nitride as a piezoelectric material over other type of available transduction mechanism. And here's just an attempt to give a brief, like a 1 slide, and I'm sure people in the audience might feel differently, but that's my own perspective, and I try to motivate it with equations even. But sort of piezoelectric is sort of the way to go if you want to make the easiest way probably to achieve miniaturization in transductions. And if you look at the force, right, so I try to express force basically assuming a constant electric field scaling law. For electrostatic thermal actuation, here you assume a constant temperature, which is a relatively reasonable assumption that you can maintain the same delta T in smaller scale devices. And as well, for piezoelectric, V over T is the electric field, so you can assume a constant scaling electric field. Well, all 3 scale in terms of dimension with the same power, beta squared. So all 3 of them should be amenable for miniaturization because they scale at a lower speed basically than body forces, right? Body forces will scale as beta cube basically, beta cube, right? So per unit volume, you substantially have an advantage in scaling these technologies. But the problem is, electrostatic is nonlinear, and especially is limited in magnitude. If you do F over A, and you calculate for all this type of technology, assuming like a few volts of electric fields across a 10 nanometer kind of fixed structure, well, you get 2 to 3 order of magnitudes higher force per unit area out of piezoelectric and thermal with respect to electrostatic. The disadvantage of thermal over piezoelectric is the high power consumption. You always need to flow current through a resistor, whereas electrostatic and piezoelectric essentially use a capacitor, so don't dissipate energy to move things, right? Whereas thermal has also issue in terms of power consumption and speed. So given the amount of forces that you're getting per unit area and the disadvantage of the power consumption, I think piezoelectric is a list in our group, and we've selected it as the material to go and to scale to the nanoscale substantially. Of course, it's not a piece of cake. There's going to be challenges, and I'll try to summarize them later. But also, why aluminum nitride over other piezoelectric? And here I'm trying to make a comparison with what the other piezoelectric materials that are out there, such as zinc oxide and PZT, which are probably the most diffused and used material in conjunction with aluminum nitride. Well, when you want to make, and here the comparison is really geared towards, nanomechanical resonator and switches. If you're making maybe other devices, maybe you have arguments in favor of PZT and switches, but in PZT and zinc oxide. But the fact that you want to make high frequency devices, probably you want a material with a high sound velocity. This is the highest sound velocity. That means that for a given frequency, you can make a device bigger, actually. So it's easier to make, ultimately. If I can basically at 1 gigahertz, I would have to make a 5 micron feature for aluminum nitride, whereas I would have to make a 2.5 micron for zinc oxide. If I go to 10 gigahertz, that becomes 500 nanometer versus 250. So the fabrication tolerances are like at least 2x better. Then there's a low permittivity, which is another advantage over PZT. That means you don't have a giant capacitance to deal with. Right? High resistivity is another advantage in terms of leakage. But we see it as favorable, especially when we make nanomechanical devices where we want a low leak rate. You don't want to leak basically current through your material. We have a very good dielectric strength and a decent electromechanical coupling, which is basically how effectively we couple mechanical into electrical energy. PZT would be the best material to pick at that point, but the advantages that you get by going to PZT don't really scale very well with size, actually. So we were able, and I'll show you some results at a 100 nanometer scale, maintain the same property that we get at 1 micron or 2 micron thicknesses, which is actually the material property that are being used to generate this table, right? If I generate the same table for PZT at 200 nanometer, this factor becomes 10 times lower, actually, based on experimental results. Theoretically, yes, you can get there, but people have effectively seen a degradation of PZT at those scales. So it might be a real challenge. And the other thing is compatibility with IC manufacturing. You'll hardly see a CMOS line accepting to make PZT devices, unless you have a deal with a ferroelectric, maybe memory device company, then maybe they can make PZT devices. But if it's a standard IC company, it will be amenable to have an aluminum nitride line run next to a CMOS line, but we'll never do it with PZT. And same thing with zinc oxide because of the zinc content. So I'll try to summarize the fact that this scaling comes with challenges, and then I'll sort of go over these challenges while I talk about the different devices and how we solve them and how we address them. So the first thing, and I think I sort of already clarified, was the selection of an effective and efficient transduction mechanism. So piezoelectric as the efficient mechanism over electrostatic or thermal, and aluminum nitride as the material of choice. Then the problem is preserving this aluminum nitride property at the nanometer scale, and I will show you some results at 250 nanometer for resonators and 100 nanometer for switches, mechanical switches, where we were able to actually preserve good orientation, and even scaling a 50 nanometer of some of these mechanical switches, for which we don't have experimental result yet, but the preliminary data on the film deposition are very promising. So there's a continuous path for miniaturization. Stress is another problem that people working with IC and CMOS generally neglect, and it's extremely important instead for miniaturized structures because they play a key role for moving structure. And so we've worked in collaboration with Teagle in mitigating some of the stresses directly in the film, and looked also at interesting things that you noticed in the device engineering, basically the way you design your structure to eliminate some of this stress, or at least make the structure less susceptible to stresses. And that's part of the basically device engineering, how you take into account now the new scale of the device. And there's nothing about quantum mechanical limits or anything like that, but there are the way you lay out your geometry, the way you slightly change your device, your actuator size, the dimension, and so forth need to be taken into account. So there is a little bit of design that actually has to be placed into the engineering of the device. And another big challenge that I think is still an ongoing challenge is really the fabrication tolerances. For that, we actually don't have a solution yet. I mean, the brute force approach will be, well, let's just wait a few years. The technology will get better because for sure we'll be making 10 nanometer nodes sooner or later, so we will be able to make our devices as well. But that might not be the best idea, the best solution. So now a little bit about the different topics, and I want to start with the resonator for RF application. So the resonator that we make are aluminum nitride devices, and aluminum nitride for RF application already is an established material actually. It's actually used for FBAR, which, as some of you may know, are already used actually in pretty much all the WCDMA phone in the US. So any Verizon phone probably has an FBAR duplexer in there. They still are struggling though to take over other markets because of the cost, but still it's a very well established material. Differently from an FBAR, which actually dilates in the thickness direction, we move laterally, and we do that through the D31 equivalent piezo coefficient. And I'll explain more later in a later slide how exactly the structure vibrates and so forth. Here's sort of a quick overview of the technology, which we achieved what we call an electromechanical coupling, so how effectively we transfer electrical into mechanical energy of 1 to 2% for this resonator. And we saw one of the big problems generally associated with NEMS devices, which is the impedance matching. So we can design now a resonator with sub 50 ohm impedances, so we can directly interface it with electronics and so forth. And then we get Qs. The highest Qs are about 4,000. Of course, those are like one of a kind. But generally, we get 1 to 2,000 for most of the devices that we make in air. Those are quality factor in air. So how the device exactly works, this is like an SEM picture showing the device. This is about what we call a 3-finger device, in which we basically apply a vertical electric field across the film thickness. And you can see how we switch the polarity of that electric field so that we can basically induce lateral expansion and contraction in the adjacent element. So you can see as an individual element that is mechanically coupled to the next one, or you could see it as an overtone of a plate. Either way will work as long as you use a 1D model. If you use a 2D model, things get a little bit more complicated and you need to take into account a real plate at that point. But still, basically you have lateral expansion and compression, and that can be modeled as a standard quartz crystal device or a mechanical resonator, same thing that you do at the millimeter scale. This is a slightly modified model that takes into account parasitics that tend to play much more of a role at the micro and especially at the nano scale. So the external parasitic actually can become comparable to your device size and can cause a problem. So you need to account for those. Generally, those are not, and RS are actually neglected in a macro scale device. In a micro and nano scale, you need to account for those because they can affect your circuit performance. And here's how the model actually fits an experimental curve at 220 megahertz device with a Q of 2100 and an electromechanical coupling of about 2%. You can see how both phase and amplitude of the admittance response of this circuit fits very well the effective electrical response of the mechanical device. So we've also made different type of devices in which we basically do not put a bottom electrode, but we just use top electrode to route the electric field. And this is an interesting solution because it really simplifies the process. My students love it because with 2 masks they can make a device essentially, right? So it's very easy, not much processing involved, and you can really get good devices. Actually, we've done it high frequency. It's very easy. You don't have alignment issues or anything. There is a drawback that I'm not going to talk about too much, but when you use this type of configuration, now the thickness, there has to be a specific ratio between the thickness of the film and the lateral dimension. So it sort of limits the frequency that you can use, the frequency range. So you basically have H, where H is the thickness of the film, over lambda, which is the wavelength of the acoustic wavelength that you want to generate, which has to be about 0.5, the ratio of the two, in order to get maximum electromechanical coupling. So you're sort of limited in the range of frequency for a given thickness that you can achieve. You have a small spread of that curve. So you cannot do like 20 megahertz to 3 gigahertz as we do with the other type of structure. So you can probably do 50% of the center frequency of your device. But you could still cover maybe 800 megahertz and 1.2, 1.5 gigahertz. Still of interest for some application. And we really have basically now a device space where we can plot basically over frequency and motional impedance how we can define different type of geometries. We use rectangular bars, which basically you have a single element of a finger, like is a single finger. We can even wrap that finger around and make it into a ring, which is a geometry where we actually almost abandon now. Despite making for good SEM pictures, it actually has this advantage of that big hole is actually a waste of space. So it's not so interesting anymore if you want to compact and squeeze many devices in a small area. Whereas this is a much more compact solution, and we can go basically from 10 megahertz to 200 with this structure, 100 to 400, and we've seen 200 to 3 gigahertz with this type of structure. And I put a limit of 3 gigahertz. I'll show you results up to 9.9 gigahertz actually with these structures. But I put a limit of 3 gigahertz in terms of manufacturability. If you're using a standard CMOS line of 10 years ago, you're probably limited to 3 gigahertz. If you use top of the line CMOS, then you can probably go to 9 gigahertz. But nobody will ever make a MEMS device with a top of the line CMOS for use. So if you want to be realistic and want to think about commercial application, that's probably a boundary that you should probably be setting. Anyway, but we're interested in scaling, right? So we want to go smaller and we want to make the device smaller, especially we want to go above 3 gigahertz. So how do you scale? Well, frequency, the equation is relatively straightforward. The equation is 1 over 2W times the sound velocity, the square root of the Young's modulus divided by the density, is actually the acoustic velocity of the material. That's constant, so you just have to scale W, right? Make W smaller, you make it smaller than 1.5 micron, you're gonna get to 3 gigahertz. But that's a problem. We've already seen that for making devices above 800 megahertz and so forth, you really need to make that array, right? But there's still a problem about 3 gigahertz. The capacitance, the parasitics of your substrate are actually starting to become comparable to the one of your device, to the capacitance of your device. So any energy you're putting into your device actually gets split between the device and the substrate. So it's a little bit of a problem. So we try to basically preserve the same area and we don't want to just make the device gigantic, which we could do, but it's probably sort of a brute force approach. But it's probably better to try to thin the device down. So you increase the capacitance of the device and you make it bigger than the capacitance of your substrate by making it thinner. But that's not the only thing you need to do. There is also a problem with the resistance. So basically you can make very thin now, you have to thin your electrode as well, and now you have very long electrode lines, right, that are running there. And that is a problem because having very long electrode lines are actually killing your Q. Basically they're loading the quality factor of the resonator by introducing an additional resistance on top of the one of the device. The impedance of the device, the RM of the device goes down because you're making it thin. So you're improving the effective coupling, but the electrical resistance of the lines become bigger, so you're really effectively loading your Q. So you really need to make your device shorter. So we completely moved around the aspect ratio of our device. Our device now, basically the width becomes the length, and the length becomes the width. And some people were skeptical about that solution because you're completely changing the aspect ratio of your rectangle, so you could introduce other modes. And it's actually instead a key advantage of this technology that despite the change in aspect ratio, we still get a single individual mode of vibration, a single peak. And it's actually very similar to what you see in surface acoustic wave devices which were developed 60 years ago, and they're based on basically interdigitated technology like this one. They're just not freed from the substrate, and they use surface waves instead of bulk waves. And that's an advantage of SAW over, for example, F-bar. Then when they change the shape or they scale it, they see other modes of vibration superimposing. So to quickly summarize the design rules, so you reduce W to increase the frequency, you increase N and T to increase the device capacitance, so you reduce T and you increase N to increase the device capacitance, and at the same time maintaining a small area. And you need to reduce the length of the device to increase the loaded Q of the resonator. And so that's what we took into account when we designed our first high-frequency devices, which are actually, these ones are based on the lateral field excitation. So we're just putting patterning electrode on the top, and the electric field gets routed through the thickness of the device. These are made out of 250 nanometer thick aluminum nitride with a top layer of aluminum electrode that are about 100 nanometer thick. And with pattern features, this feature was done with E-beam lithography. We don't have a stepper that has this kind of capabilities, but we use basically a last step by E-beam, right? I mean, in a CMOS foundry, making 300 nanometer is not a problem, right? It's not a big deal, but it was for us, so we had to interface the E-beam to the standard stepper. That was a minor issue, and we can make basically these high-frequency devices, which, if you look at them from far away, like, they look pretty big. They're 50 micron by 17. But if you look inside the device, basically you have a 300 nanometer feature now that is excited in lateral vibration, either expansion or contraction, by changing the polarity. And we basically arrayed up to even 99 of these devices to make our highest frequency device. This one has 99 fingers and 9.9 gigahertz. And what is interesting is that the model stays the same. You get the same type of devices. Here, the RM wasn't properly designed. We're getting actually 800 ohm in this reported, the one that was reported at the conference on NEMS 09. We really can make now 100 ohm or 50 ohm, even at this frequency, even at 8.5 gigahertz. And what's very interesting is that the Q is actually relatively high. I mean, we're getting like Qs in the 500 to 600 or 700 even at these frequencies. So it's quite interesting. The Q in vacuum goes up just a little bit, as we suspected anyway, because we don't see basically much of an improvement when we go up in frequency. The molecules don't even have time to basically respond to your frequency of vibration. And the FQ product, which is actually the highest we've ever recorded in this mechanical structure. So apparently we scale, and you can see the FQ product, which is one of the figure of merit of our devices, beyond the KT squared Q product. It's probably a more important figure of merit. But anyway, the FQ product is an important one, and you can see how we achieved the highest FQ product at higher frequency. We didn't effectively increase the Q, but we sort of maintained the same Q almost even at high frequency. So it's interesting to see how making it smaller doesn't really hinder us. We could harness at that point the advantage of making the device smaller for sensing application, as I'll show later, because we are improving the sensitivity of the device, but we're not reducing its minimum detectable frequency shift because the Q stays the same. So you can effectively improve the limit of detection of your device, for example. And you can explore basically doing similar solution with a high Q element even at high frequency. Another interesting thing that we've seen when we scale the devices, and I'll briefly talk about it, is the power handling. We get a lot of questions about power handling, so one of my students actually started doing some tests and measuring, basically using a simple mechanical model, a 1D model, tried to compare the 1D model, mechanical model, to the actual electrical response of our devices, and measure basically what's the critical current that you get in your device at the maximum power that you can apply. And he saw that basically stereo was matching pretty well with the experimental data. And actually we derived a scaling law for this critical power that per unit area scales as the thickness of the film inversely proportional to the Q squared and the frequency. So the higher the frequency, the higher the critical power that you can put in your device. So it's true that you're losing a little bit in thickness because we've seen that to go to higher frequency, we really need to make them a little thinner. But the frequency is an advantage. So basically going to a higher frequency, even per unit volume, is independent of thickness, right? So per unit volume, you really have a gain, a net gain in going to higher frequency in terms of power handling of the device. And that's maybe people might think is counterintuitive, but actually scaling and going to higher frequency is advantageous in terms of power handling. And that's demonstrated experimentally also, so it's confirmed. So a couple of other things about real application of these devices. I want to show you. These are really not, the filters actually we pushed them already in the 3 GHz range. The oscillator, I'll talk about 1 GHz oscillator that we made. Really real basically insertion into circuits and using a circuit element of this type of devices. So the oscillator actually we used a simple Pierce design. Is the most simple oscillator circuit you could ever design. It requires basically a single transistor. We're using 2 here to just increase the efficiency. We're using basically a PNN and a biasing resistor, M3. So it's very simple actually, and then there's a buffer that we have to design. And we just hook up our resonator via wire bonding to this device. And we made this first CMOS chip in a 5-volt half micron technology, so a relatively old technology, but still we can sustain gigahertz oscillation. And that's the key problem though of the 3.5 milliwatt power consumption. We think we can go much lower actually. We can definitely go in the microwatt range with this type of device if we just add a better technology, which we are actually, my student is actually now trying to get access to 65 nanometer technology, and we're going to try to make actually CMOS out of a 65 nanometer and design basically microwatt kind of level, power level. And the output power is still relatively low. That was due to inefficient, some mismatch basically between the impedance of the resonator and the impedance of the circuit. So we really didn't put all the power that we could have in the resonator, which we could have actually definitely even further improved the phase noise performance of the device. So we're monitoring the phase noise as a key performance spec of the device using a signal source analyzer from Agilent. And here's actually the response, the experimental response. We get a floor of about 146 dBc per hertz. This is at 1 gigahertz, so it's a 105 gigahertz, sorry, it's a 105 gigahertz oscillator. And this is the offset from the center frequency. So above a megahertz, you're hitting the noise floor, and we were getting about 146 dBc per hertz. This is mainly limited by the power handling of the device. So I told you minus 23 dBm of power output wasn't really optimized. So we could really push this even lower, probably to 160 dBc per hertz, which would probably make it one of the best oscillator out there at 1 gigahertz. And 81 dBc per hertz is actually a respectable performance at 1 kilohertz offset. It's still not good enough to make a VCO source that doesn't need a reference, a quartz crystal at that point, but in a PLL loop. But it's promising, and here if you look at the GSM requirements actually for a high frequency VCO, well, you can see that we're already making best specs in terms of noise floor. Of course, our ultimate goal would be to use that individual resonator as the reference without putting it into a PLL loop with a crystal reference, so you nearly need to lower that noise in this range. And another way to compare, actually we put together, basically we use what is an accepted figure of merit for this oscillator, and basically it takes the phase noise at a certain frequency offset, scales it for the frequency of operation and for the dissipated power, and creates this figure of merit which is measured in dBc per hertz. And actually we compared with other oscillator made at 1 gigahertz or in the neighborhood of 1 gigahertz. I can see 1 to 2. And you can see how we're basically superior to any other, comparable, I would say, to any other mechanical device that is commercially available, like a saw on an F-bar. And definitely better than LC based, and that's just because of the amount, the Q levels that you can achieve with these mechanical structures. So we've also went ahead and made filters. This is a low frequency type of device where we actually have integrated with a mechanical switch. I'm not going to talk about too much about the switch because I want to show you the miniaturized version of it, and I'll be talking about it later. But it's really basically a mechanical element that is used to turn on and off basically a filter. And we've actually monolithically integrated with the NEMS filter, and you can see that we can really turn on and off our filter. So with more than 50 dB of rejection, basically, from the on state to the off state. And that's done all on the same chip. But as I said, it's all about going to higher frequency and miniaturization. So we've taken some of those devices that I've shown you before, and we try to make it into a filter, a very simple element. It's just a second order filter, but we use the intrinsic capacitance of the device to couple one device to the next. And that's fine, but the problem is that when you scale with frequency, that parasitic capacitance that unfortunately exists also reduce your effective coupling and degrades the performance of our devices to the point that we're not getting actually fantastic performance at 3 gigahertz. Yes, you have some sort of a filter response, and you have small impedances and everything, but your insertion losses are really the key problem, and they are affected. Here we get basically more than 10, about 11 dB of insertion loss, which is relatively large for a filter of that frequency. But you can see how much that's affected by the parasitics. So if you design around the parasitics, either by directly integrated with CMOS or by redesigning the capacitance of your device, actually, you could design the capacitance bigger than the parasitic capacitance, so that at that point you can really lower, with the same device, if you were to remove those parasitic, basically your insertion loss would be going down now to about 6 dB, which wouldn't make it still the best filter available. For such a narrow band, a band of about 0.3%, which could be good, for example, for WLAN channel selection, well, then those insertion losses might become acceptable. And really, I mean, this is the real first prototype. If we increase the Q, right, the Qs are still in the 400 range. If you could still get a Q of 1,000 at that frequency, then we can probably make, at that point the insertion loss would go down to another 3 dB, basically to 3 dB, making a very acceptable filter at that point. So the other topic I want to mention about is actually the sensor arrays, and we're involved in a project that looks at basically creating this mechanical array of resonator that potentially could be interfaced wirelessly, and we're trying to do a functionalization process with an original functionalization based on nanotube plus DNA, where the DNA library basically allows you to do selectively detect different species. What I'm focusing on today is really the aluminum nitride transducer. This is a research in collaboration with a colleague in the physics department who has already demonstrated his working principle with carbon nanotube transistors. We're trying to apply now for gravimetric detection as well. So basically it's the same resonator technology that now we want to use for sensing application. But so why using it for sensing? I mean, when you look at a sensor, there's several things that you're looking at, and especially the limit of detection, the sensitivity, basically the dynamic range. Can you detect, like, if you're detecting mass, for example, can you detect micrograms and zeptograms at the same time? So you would like to have multiple sensitivities. And at the same time, you probably want to make it into a functional device that you can actually interface with electronics, and you could actually ultimately sell and be used somewhere. And ultimately a small form factor. Because if you look at the existing QCM, quartz crystal microbalances, and SAW, quartz crystal microbalances are cheap and they're used for making basically reference crystals in any electronic. SAW are used for making filters in almost 80% of the phone nowadays. So this should be the technology you should be using if you want to make a sensor. But it's really not, because they can give you sort of the same performance, but they're not small, they're not miniaturizable. And I think the true revolution that you'll get at the nanoscale is not going to be in a real gain in performance, but in a real gain in miniaturization. So in making basically multiple devices on the same chip in a small form factor that will solve the problem of selectivity substantially. That is the key problem of a sensor. You can't make an array of quartz crystals. It will be as big as this desk if you make 1,000 of those devices, right? But you can make 1,000 of these devices and still fit it in a millimeter. I mean, not a millimeter, but for sure a centimeter square. And that, I think, is really going to solve the problem of sensor arrays and making basically noses and so forth. So that's why we sort of select this Contour-Mode Resonator as the key solution, because it embeds all those different characteristics over 3 of the miniaturizable solutions that are out there. So how do you make a sensor out of this device? Well, I've shown you already the frequency equation. Well, if you look at sensitivity to mass loading, it's a simple derivative of the frequency with respect to the mass per unit area, concentration, right? You always want to detect concentration, not just mass. A useful chemical sensor will detect concentration, will not detect mass. Okay? So you get basically an equation that scales as the frequency square divided by this type of constant. Well, it turns out that given our geometry, that equation assumes that you're perturbing the direction of vibration. Well, we can't do that in our resonator. We would have to put basically the absorbing layer on the thickness. we're better off putting it on top of the device, on the top surface, which actually turns out to be an advantage even more, because now the W/2 ratio is generally greater than 1 for us. So the sensitivity of the device even goes up. And you end up with now a sensitivity equation if you express frequency as a function of W, that basically depends on frequency and inversely proportional with thickness. So you probably already understood that if you make it thinner, the sensitivity will go up. If you make it higher frequency, the sensitivity will go up. When you make a sensor, sensitivity is not the only variable though in the game, right? It's actually the limit of detection that matters. But let me compare first sensitivity to mass loading of a contour-mode resonator to an F-bar, which I think is our closest competition. F-bar or quartz crystal, basically a device that vibrate across the thickness. They use the thickness to set the frequency. Well, if you look at our sensitivity, I've already told you that frequency and thickness are the two key parameters. For an F-bar, it's just frequency, because frequency and thickness are related. So when you scale the thickness, you're also scaling the frequency. So instead, for our devices, you can independently set the sensitivity from the frequency, right? Once you set your frequency, you can adjust the thickness to adjust your sensitivity level. And that's unique because there are applications in which, for example, you want to design a sensor of 433 megahertz, which is one of the standards, or 920 for the ISM bands. Well, you really need, at that point, a certain sensitivity level and a fixed frequency. With an F-bar, you'll be stuck. With a quartz crystal, you will be stuck at that frequency and with that sensitivity. Here, once you have the frequency, you can still set the thickness independently. But it's not just that. There's, as I said, the ultimate thing is the limit of detection, right? You could have an extremely sensitive detector, right? But if there is noise, it's also equally noisy. Well, then you didn't gain absolutely anything except making probably easier your detection, right? Because you're going to get larger, you're making it easier on the electronic, but your sensor will not be able to detect smaller variable just because it's more sensitive, right? It's the noise what matters. It's the limit of detection, which is actually the ratio of the minimum frequency shift that you can detect divided by the sensitivity. So we're monitoring. Actually, maybe I did not clarify that in the audience, but we're using the resonator as a balance, substantially. Adding mass to the resonator will change the resonance frequency. The resonance frequency of a mechanical element is always the square root of K over M. So if you're adding mass, you're changing the frequency. That's the principle of operation. So what you're monitoring is frequency shifts, right? And you want to detect the minimum possible frequency shift. Well, the minimum detectable frequency shift is generally proportional to the center frequency divided by Q. So if you compare this to technology, well, you're getting that now the limit of detection, if you assume that you can maintain the same Q, is going to scale with the thickness. So it's going to get smaller with a smaller device if you keep the same Q, which I will prove you in the next slide. It's possible. But for an F-bar, well, the FQ product is constant. So it doesn't matter. It doesn't matter if you make a higher frequency device. The limit of detection will stay the same. Whereas here, if we make a thinner device, we can actually increase our limit of detection. We can lower our limit of detection and increase the performance of the device. So here's an example of a pretty big resonator that we made at the nanoscale. This was poorly designed actually because of the 200 micron length, right? That's loading the Q, and I will show you actually experimentally that it's really loading the Q. But here's the mechanical response, and we can fit it with this circuit. Yes, the circuit is the same. The problem is this RS is pretty large. It's actually comparable to the RM, the mechanical impedance of the resonator. But the mechanical Q of the device, if you just look at the LCR, is still 1,000. And the electromechanical coupling is still the same. So this is a 250 nanometer thick film, which basically has maintained similar performance of the 1 or 2 micron thick films, but now is 4 or 10 times thinner. So it will have 10 times the better limit of detection of a higher frequency device, of a higher thickness device. And this RS of 28 ohms is, as I probably understood already now, is due to the fact that we have long lines and metallic vias that probably did not work the best during that fabrication run. So in terms of functionalization, we're using this novel functionalization layer in which we've grown some nanotubes on the resonator, and we then attach single-stranded DNA to the resonator. And I'm not going to focus too much about this. I'm just telling you that we have a scheme basically to differentiate between different type of analytes based on the different strands of DNA. So the sequence of the DNA can bond to different gases, to different analytes, depending on that type of strand. And you can play, now you have basically an infinite library given time, on a certain amount of time, and probably a good molecular dynamics simulator. You could actually simulate the bonding between gases and DNA and possibly predict the affinity between the two. So what we've done also, we've connected, and this is a work that will be presented at NEMS 2010 actually, we connected this resonator, the thin one, the 250 nanometer, to an oscillator, the same oscillator actually. And actually it works very well, so it's actually interfaceable with electronic circuit. And we functionalized it with DNA as well, but we did not grow nanotube on this one. We didn't want an extra challenge. On top of that, we just used gold and attached a phyolated DNA to the gold. It works as well. You probably lose it a little bit in surface area, the advantage you have with the DNA, but and we connected to a Pierce oscillator. We monitor with a spectrum analyzer. Probably not the best way to do it. You probably want to have a frequency counter to do that, which we're going to do soon, to monitor basically the frequency shift. And here's the response. Basically, we use DMMP and DNT with two different strands of DNA, and you can see how the DNA the DNA basically enhances the response to DMP and DNT. So if you now imagine having 100 of these devices with 100 different strands, well, you can get different type of signature depending on the strand of DNA that you have for different type of analytes. There will be yes or no kind of responses probably, but you can also get quantitative information. Thanks to the fact that we connected now to an oscillator, we can really start estimating limit of detection. And in particular to DMMP, we have about ppb, hundreds of ppb, and to DNT, we have about 5 ppb. And that's mainly due to the affinity of the DNA to DNT. Those are actually not experimental data. Those are extracted based on the actual response, the response to the device. We are actually having problem flowing those low concentration right now. It's not that our device probably cannot detect them. It's actually we cannot flow the small concentration right now. So we're building a better setup to do that. One last bit about this resonator in liquids, because if you're thinking about sensor, well, maybe you're thinking about biosensors as well. And I think actually the biggest revolution will be in the bio area for this type of sensors. And so we start putting them in liquids and look at the performance in liquids and look at that Q basically, which is basically setting the limit of detection. And what's interesting is that both theory and experimental data sort of match. Well, there's a discrepancy, right, between experiment and theory, but there is a trend at least. There is an increase that the theory predicts as a square root of f, just a simple oscillating plate in a liquid. So going to higher frequency can actually improve your Q in the fluid. And because of that, now going to higher frequency improves your sensitivity, your Q goes up as well, so you could potentially really improve the limit of detection of your sensor. Far away from demonstrating a real device, but we're working in that direction. Last part of the talk is actually a quick overview of nanomechanical actuators and switches. So this is another area of effort in which we're basically making those mechanical computers that I mentioned about at the beginning. And the idea is to really make a mechanical switch element that is based on two opposing cantilever beams, basically, that are actuated via piezoelectric film to bend up and down. So substantially, we can induce contraction and expansion in a bimorph layer. It's a simple bimorph actuator that probably most of you are familiar with. You basically apply an opposite potential, one contracts, one expands, and therefore you have bending of the beam. You can either open or close depending on the polarity of your voltage. And then we have a signal line that routes the signal, basically, and the two gates placed on the left and right of the signal lines that produce the actuation force. The problem is this has already been, we demonstrated at the MEMS scale, it works very well. Well, to go to the nanoscale, produce those very small form factor devices with very low voltages, well, we need films now that are 50 nanometer or less. So that's a big challenge in scaling. And another challenge, which is actually not, I think is less of a challenge than making the film thickness, is defining gaps that are now, excuse me, 10 to 40 nanometer in thick, in gap size, basically the air gap size. So the key challenge is actually miniaturizing those films, and when you deal with those films is maintaining the quality of the piezoelectric element. Depositing a 50 nanometer film is not a big deal. but making it piezoelectric is another story. So what we do so far is monitoring the full width out maximum, which is basically a measure of how well-oriented the material is. Below 2 degrees, we consider to have a very good piezoelectric material. Below 5 is still a piezoelectric. It will not work very well probably for a high Q resonator, but will still work for a mechanical actuator. At least that's what we've seen in correlation in experiments based on data on full width out maximum and experimental data on mechanical resonator and switches. And here you can see that if you do 100 nanometer, we still get on platinum, which is ultimately the material we care about, the metal electrode, we get rocking curves below 5. So it's promising. 100 nanometer is right here. This is actually, I think this is 50 nanometer on silicon. We get a rocking curve less than 3. So we can probably stay below 3, below 5, even on platinum, and we believe we can make actually mechanical actuators. I mean, 100 nanometer is 4.5, and I'll show you now that it has exactly the same performance of a 1 micron or 2 micron thick film. The other big problem was stress. Apparently, we get huge stresses when we deposit small thin films. We can control very well the in-plane stress to plus or minus 100 megapascal, but the stress gradients are huge. These are actually like probably the best results, 300 megapascal. We sometimes get 800 or 900 megapascal per micron. But with heat treatment, and this is actually a work done by Teagle, we're collaborating with Teagle on this thin film thicknesses. They basically warm up the wafer during the deposition process. They can actually lower the stress down to a few hundred megapascal per micron. It turns out that actually maybe 500 megapascal per micron is something we can deal with at the nanoscale. Because if you run the numbers, the structure is smaller, so it's a lot stiffer. So it will displace less for the same stress gradient. So maybe it's not going to be such a big problem. And for 100 nanometer thick, we also looked at the electrical characteristic of a large frequency range, because ultimately this device will be used to switch, right, mechanical elements that signal in the hundreds of megahertz, hopefully gigahertz range. And the dielectric constant of these films actually stays pretty much constant across the entire frequency range. And the leakage also is very interesting, is very small, 0.4 nanoamps per centimeter squared at 1 volt. This actually makes it better than a silicon dioxide, 100 nanometer thick silicon dioxide. So the gate, the oxide of your gate transistor, right? So the leakage characteristics are comparable. It shows that it's low leakage, and therefore will probably be good for making those mechanical elements and reduce the off-state leakage as well. But we went ahead and make a NanoActuator. It's basically half part of a switch, which is basically your mechanical actuator. It's a bimorph. We actually stacked 2 100 nanometer thick aluminum nitride layer on top of each other, sandwiched between them platinum electrode that were 50 nanometer each. So it's a 350 nanometer total thickness, and we vary the beam between 5 and 18 micron long, and for all of them actually we got a pretty consistent curve that matches the FEM simulation for a given bulk-like piezoelectric material. So we're getting a D31 that is actually the coefficient that we use for the transduction, the effective coefficient, but is actually comparable to the microscale films. So very promising for miniaturizing this device. And then I told you that we can make logic with this type of the mechanical element. So, well, we haven't made it with the nanomechanical, but I'll give you a quick overview of what we'll be presenting at IDM and NEMS, just as a brief introduction. Well, we can really we've proven the concept basically at the microscale. By using what is called a body biasing technique, which is exactly the same body biasing technique that you use for making, they use in a CMOS transistor, but now you can apply a much larger voltage as a body bias, differently from a transistor, where you can really switch with now threshold voltage in the order of millivolts. And what's very interesting is that you can make a P or N-type transistor out of the same mechanical device by simply changing the polarity of a bias. So I can make basically an N-type or a P-type out of the same mechanical element. You're solving the problem of symmetry that you generally have in the CMOS and the different scaling of devices in order to make them the same, handle the same current. And we went ahead and made mechanical inverter by wire bonding 2 of these mechanical elements. So here's the response of a similar device. Here is actually an inverter that is switched with 1.5 volts on and off, a mechanical inverter. And here, the transfer function of that mechanical inverter, and if you are a logic guy, you realize immediately there's a problem here because this is too big, right? Basically becomes a tri-state kind of logic device. Well, this at a VT of 3 volts, right? We have VTs of 1 volt, and if you can really make reliably those VT of 20 millivolts, this region will substantially disappear. Really make it a 2-state logic like you have in CMOS, but now with a threshold voltage of hopefully 20 millivolts or 30 millivolts, not anymore a 1 volt or 0.7 or 0.5 millivolt threshold voltage. So a lot lower power consumption in the on state. You basically can think of this transistor as substantially a delta V around a biasing voltage. So the energy you need to charge and discharge your capacitances are like a small amount. It's just the delta V that you need to turn on and off the transistor. And even we start to make a little bit more complex structure, even by scaling the thickness. So we made it 250 nanometer. So these are actually operated with now a body bias of 5 volts and just 1 to 2 volts, actually 2 volts operation. And we can do that, we can build NAND and NOR gates, actually, with this type of mechanical elements. So it's quite promising. Of course, the switching times is not excellent, but we think we're switching actually. The turn-on time of the best mechanical switch is about 80 nanoseconds. We want to go around that with the full delay time. Basically, we would like to have a delay of 100 nanoseconds or so. But the miniaturization will help. We'll make the device faster and will help in that. So to summarize, I hope I did a good job convincing you that NEMS resonator and switches will actually enable a new entire realm of application for low power and reconfigurable RF application, chemical sensor arrays, and computing. I think there's really promising performance and demonstration that we can get by scaling the technology. And then some, I think, interesting results on the aluminum nitride results you've seen, the resonators, both for RF as well as very high sensitivity sensors, as well as some initial results on these NEM actuators that are really setting the pathway for these ultra low voltage logic elements. Of course, there are many, many challenges ahead. This large-scale integration still remains a dream, but hopefully it'll be possible in the next 3 to 5 years. Fundamental science of these super high frequency resonators, right? Q is not fully understood. We need to improve those quality factors, long-term reliability. Nano switches, we can make 1, we can make 2, but contact reliability, I didn't even talk about it. It's a problem, it needs to be solved. So there's still open challenges that needs to be investigated despite the promising results. So this I like to conclude and acknowledge especially the people in my lab who are actually doing all the hard work. That's the postdoc and many of the PhD students actually, and several collaborators at Penn and Berkeley, and collaboration with companies as well, Teagle, and the funding agency that sponsor the work. So with this, I thank you very much for your attention. And
Do we have time for a few questions? So the floor is now open for anybody. Yeah, right here, Bobby.
Have you tested your miniature switch in a harsh environment, like or just testing?
so we're testing right now for the long-term reliability. We just started testing. We're starting them in a nitrogen environment. So we build a chamber and we're flowing nitrogen in it. But harsh environment, we've never done it. It's something that I actually would be interested in doing. And I know you guys are big experts actually in harsh environment with silicon carbide. And I think actually aluminum nitride would be a promising material for doing those because it doesn't. Another thing over PZT, for example, it doesn't dipole at high temperature. So you can really operate at 500, 600 C. We've grown nanotubes at 1,000 C on the resonator and then tested the resonator and it was still working as before. So you could really make high temperature, I think devices operating at high temperature, probably high pressures and everything. So I think it would be a promising material to look at. Or it could be a transducer for a silicon carbide device. That's another thing. Given silicon carbide might have some exciting property for high Q at high frequency. So.
Can you go the other way to very low Q, like Q of 1?
Q of 1? Yeah, oh, that's easy. Like, for the mechanical, that's an interesting question at the same time. For the mechanical switch, having a Q of 1 might be ideal, actually. Maybe not ideal, but 1 to 10 would be probably the best way to do it, for basically avoid bouncing problems, right? And the risk is that with this nanomechanical structure, you're going to inevitably get a Q of 100 or something like that. So, but loading it is something that I think we can get pretty good at pretty easily. Raising the Q is much harder because it requires beating some fundamental physics law. Degrading the physics law is a lot easier. So Q of 1, you could do it by simply mechanical loading, clamping the structure more, and so forth. Is there an application you had in mind, or?
Yeah, you want to get a monopole.
A monopole? Like, you're saying a broadband?
The impulse response will be an impulse.
The impulse response will be an impulse. And that you can get it just with a Q of 1?
You have vibrations all over the place.
Sure.
And I want just a very narrow pulse. You know, traveling through the sky.
But that's in the frequency. Oh, in time domain, you're saying. A narrow pulse in time domain. Okay. Yeah, but then you lose your selectivity, right, in terms of frequencies.
How about other materials, you know, like tantalum, nitride, like
maybe we...
titanium nitride.
I mean, I don't think it's actually... These are mechanical cues, right?
No, I'm talking about, you know, okay, forget the monopole. The material that you use, aluminum nitride, that's a part of a very large family, tantalum nitride.
Oh, you're saying the 3-5 essentially. So actually, nobody has ever explored the piezoelectricity in tantalum nitride and titanium nitride. I don't think actually they are piezoelectric. I've never looked into that. That's actually an interesting thing to look at 3-5 in that sense, because actually it depends on the lattice. And is it Wurtzite structure as well? I mean, it's like a hexagonal lattice.
Pretty much, yeah. Most of the big capacitors are like this. You know, tantalum capacitors, they are all a part of the same.
Well, a single material will not work. If it's tantalum nitride, then it might because of the hexagonal structure. But then you need to orient it, right? All the tantalum nitride and tinitride, those are amorphous films that are put down.
Yeah, amorphous film.
Generally, ours is a polycrystalline, right?
What's the grain size?
So the grain size is about 10 to 20 nanometer, and we get decently oriented polycrystalline film. So we have to have a preferential growth direction of orientation in the C-axis, basically perpendicular to the plane. Otherwise, you will not get piezoelectric effect in the film. So this, I mean, it might be possible actually that tinitride might be piezoelectric, but the problem is making them well oriented. And I don't think there is a technology yet out there. I mean, another reason why aluminum nitride is a good material is because there has been 10 years of development by a large corporation like HP that then made the F-bar and made it really in a reproducible material that engineer can use and develop.
We probably should try to field one more question before lunch. Nick, did you have a question?
No.
He's just scratching his head. Anybody else have a question before we adjourn? Because I know there's going to be pressure for lunch. I have a few questions, but I can save them for lunch. I have that advantage. Chris has
I know with NEMS resonators, anchor loss is something you look at. Have you had time to analyze the effect of your anchors on the mode and resonator?
So that's a very interesting problem, and I actually believe that anchor losses are a big problem for our devices. Have we looked at it? Barely, not enough actually. And we have a new program, hopefully, the DARPA program, that will allow us to actually model everything. Now, there's COMSOL simulation now that allows actually with this perfectly batched layer, boundary layer, to actually simulate these anchor losses and everything. So we're going to look into that and try to see if we can get improvements. What is very strange is that we basically try to make devices that are fully anchored, so essentially no tether connection, and we still get a Q of 1000 out of those. So that might be a better way to make a robust structure, actually. But the real thing is that it probably is just below a certain scale that you see an improvement in Q. When your anchor becomes less than 2, our anchors are always at least 3 to 4 microns. If you could make an anchor that is 500 nanometer or less, probably you do see an increase in Q. And I think that's what they've seen with even the electrostatic MEMS. I mean, they claim that the difference in Q might be due to material for us with piezoelectric, but I looked at in which devices they get Q of 10,000 or above. It's really when they're basically, the tether size is below 1 micron, which we've never done actually in our structure, because the yields become 1 out of 100, and the students are not very happy about looking at one, testing 100 devices to get one that work. So.
All right, I think what we'll have to do is adjourn here. Let's thank Dr. Piazza. One of the grad students would be so kind as to bring the clipboard up to the front so we can make sure we get back to the department.